Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. All right, lecture 6.1, Geometric Objects and their Algebraic Representations, part of the Intro to Kinematics and Rotation Matrices chapter. The three-dimensional Euclidean space contains various useful geometric objects. And they are points. For example, the point P, see figure 6.1, which is at the bottom of the page, and we'll be demonstrating several of these basic geometric objects in the figure. Free vectors, that is, objects described by a length and a direction, but without a base point. We do not assume that the free vector is attached to any specific start point. Vectors fixed at a point, that is, vectors with length, direction, and base points, and therefore equivalent to an ordered pair of 2 points. These are sometimes called fixed vectors. Reference frames. A reference frame is a pair, sigma, say 0, 0 being the name of that reference frame, which has O and a set of X, Y, and Z, where O0 is a point called the origin of the reference frame, and the set X, Y, Z, all not, is a triplet of unit length orthogonal vectors, or unit vectors that are orthogonal, at the origin and satisfying the right-hand rule. Recall that two free vectors are orthogonal when they form an angle of pi over 2. All right. Vector products between free vectors. Two different notions of products between free vectors are useful. In what follows, V and W are two free vectors. The dot product between free vectors, or scalar product or inner product, different names for the dot product, is defined as follows. The scalar quantity V dot W is equal to the length of V times the length of W times the cosine of the angle between V and W. This is sometimes called the geometric definition of the dot product. 2. The cross product between free vectors, or outer product, sometimes called, is defined as follows. The free vector V cross W is equal to the free vector 1, whose length is equal to the length of V times the length of W times the sine of the angle between V and W, and 2, whose direction is orthogonal to both U and V as given by the right-hand rule. So this is my right hand, even if it's mirrored for you, I'm not quite sure. V, W, the direction of the cross product is my thumb, my right thumb. Got to use your right hand. Doesn't work if you use your left hand. All right. Note, the dot product is a scalar number, whereas the cross product is another free vector. Okay? It's important. Another note, both the dot product and cross product are defined without any reference frame. Using these products, one can define orthogonal and parallel free vectors. Two free vectors are orthogonal if their dot product is 0. Two free vectors are parallel if their cross product is 0. Really nice properties. Note, a third and final note, an axis is a unit length vector. The dot product of a vector with an axis is the length of the projection of the vector onto the axis. Representing vectors and points as arrays. In this and later chapters, it is important to distinguish between vectors and arrays of numbers. A free vector and a vector fixed at a point, or a fixed vector, are geometric objects. So they don't require any specific coordinate system. Okay, they're coordinate-free definitions. An array, on the other hand, is an ordered arrangement of numbers or quantities. An array has entries or elements or components, usually real numbers. There are column arrays and row arrays with any number of entries, for example, 2 entries or 3 entries. The transpose of a column array is a row array, of course. A matrix is a double array, or an array of arrays, depending on how you look at it. Given a reference frame, we will now review how a free vector can be written as a column array whose entries are then called the coordinates of the free vector. Often one denotes free vectors and arrays with the same symbol, but you should be able to distinguish between them and understand what is meant by the context. By introducing coordinates, we study how to represent and manipulate various geometric objects, points, free vectors, frames, etc. via algebraic equations. So we have geometry and we have algebra here. Okay, they're to be distinguished, but they do complement each other fairly well. That's why we use both. Okay, let P be a point in three-dimensional space, V be a free vector, and sigma 0 be a coordinate system or a reference frame, as in figure 6.1 above. If we go back up here, this is that figure. Okay, that's the reference. Let the vector between O0 to P denote the vector from O0 to P. The coordinate representation of V and P with respect to the coordinate system or reference frame sigma 0 are V, see the superscript 0. It's not raised to the power of, it's a superscript 0, which means that it's being written in a coordinate representation. The coordinate system or reference frame is specifically sigma 0, which is denoted by the 0. And it is equal to the first element of the array is v dot x naught. X naught is the unit vector that makes up part of the frame. Okay, it's one of the unit vectors that define the reference frame. V dot y naught is the vector dotted with the y unit vector, and v dot z naught is the vector dotted with the z unit vector, which is to say the first, second, and third components or entries in this array are the amount of v in the direction x, the amount of v in the direction y, and the amount of v in the direction z. Similarly, you can also represent a point P, which is another geometric object. You can denote it in a specific reference frame, the 0 reference frame in this case. So P with superscript 0 is, by definition, the vector O0 to P, okay, which is a geometric object expressed in the 0 reference frame. And what we do is we just take that vector from the origin to that point, P, that we're trying to write in its coordinate representation, and you dot it with the x unit vector, the y unit vector, and the z unit vector to get the three components that will represent P. In other words, it is possible to decompose a vector or a point into its components along the three orthogonal axes as V. So you can take the dot product of V with x naught as we did above, but now we will multiply it by x naught, which is to say is in the direction of x naught. This is where the fact that it's a unit vector will look familiar to you. If you're familiar with IJK notation, this is very similar to the IJK notation for a vector in 3 space. And similarly, you can do the same with the point. Given two vectors, v and w, with coordinates v0, which is to say v1, v2, and v3, and w0, w1, w2, w3, it is possible, see the exercises, to verify that if you take the dot product of v and w, it is equivalent to using the reference frame 0, taking the transpose of v and multiplying it by w. Which is to say to take the scalar or dot product using the arrays, okay? Taking the scalar or dot product in array form is equivalent to transposing this array and doing regular matrix multiplication, which will be a 1 by 3 times a 3 by 1. You'll get the outer dimensions. The inner dimensions will collapse. You get a 1 by 1 out or a scalar out here. So you multiply the first components, the second components, and the third components, and you sum them together. Similarly, we can do something like that with the cross product. In this case, if you're going to express the cross product of v and w in the reference frame 0, it is equal to this vector. This is one of the ways of representing a cross product in coordinates. Already now, interesting questions begin to arise. For example, how would you show that the dot product between two free vectors is independent of reference frame in which the free vectors are expressed? So the dot product and the cross product should be independent of reference frame. How would you demonstrate that? That's something we could look into using what we've seen so far. Here are a couple remarks. First, on rotations and translations of basic objects. Although the representations of points and free vectors are identical, remember that points may be translated and free vectors may be rotated. But it makes no sense to rotate a point or to translate a free vector. Okay. Causes a lot of confusion if you just look at the algebraic representation. All right. Remark 7.2, a little longer. Geometric and algebraic viewpoints. In summary, kinematic concepts can be understood using two equivalent languages, a geometric and an algebraic viewpoint. The geometric viewpoint is described by points and free vectors in space as basic objects, properties independent of reference frames, and concepts and tools from Euclidean geometry. The algebraic viewpoint is described by arrays and matrices as basic objects, computations in a specific reference frame, and concepts and tools from linear algebra and matrix theory. The two approaches are equivalent once a reference frame is selected. It is, however, very useful to understand both approaches and their equivalents. Typically, a geometric understanding is easy to attain, and then the geometric intuition leads to the correct algebraic equations. All right, see you next time.